Hi everybody. In this video, we're going to talk about evaluating limits at infinity, which means that x is going to be approaching positive or negative infinity. Okay.
Rashawn Holmes, if you're in the building, please report to the front office. Your ride is here. Rashawn Holmes, to the front office. Your ride is here.
Okay, so basically we're trying to figure out what is happening to y as x gets really big, meaning approaches infinity, or gets really small, meaning approaches negative infinity. Okay, which basically means what is the end behavior of the function. Okay, what's happening way out at the end. So here are some examples where we're just looking at the graph to evaluate the limit. So let's say we want to find the limit of x squared as x approaches infinity. And these are all parent graphs, okay? These come from your 9 parent graphs. So x squared is a quadratic. The graph is a parabola. And so basically, if we're trying to evaluate the limit as x approaches infinity, we're talking about this end of the graph, okay? So as x goes to infinity, what's happening to our y values? Well, in this case, they're going to infinity. So as x goes to infinity, y goes to infinity. So this limit would equal infinity, okay? As x gets really big, y is getting really big. All right, let's look at the next one. We want to find the limit of x cubed as x approaches negative infinity. Okay, so as x goes to negative infinity, what's happening to our y values? Well, in this case, they're going to negative infinity. So this limit would equal negative infinity. Okay. All right, and then we have the limit as x approaches infinity of e to the x. Okay, so this is the graph. This is your exponential function. So again, as x gets really big or goes to infinity, what's happening to our y values? Well, they're getting really big. So they're approaching infinity. So this would equal infinity. Okay? So again, when you're evaluating limits at infinity, you're asking yourself, what is happening at the ends of these graphs? What is happening to y as x gets really big or really small? Okay? All right. Now, since we know to evaluate these limits, we have to find the end behavior. We're going to look at some different functions. Okay? We're going to review end behavior of polynomials, because if the function is a polynomial, then to evaluate these limits, we just have to know the end behavior. Okay, so with your polynomials, your end behavior is determined by the degree, whether the degree is odd or even, and also by the leading coefficient. So whether that leading coefficient is positive or negative. Okay? All right, now remember, graphs of polynomials basically are smooth, continuous graphs. They don't have any breaks in them. From your parent functions, we're talking about like y equals x, which is a linear function, y equals x squared, which is a parabola, y equals x cubed, y equals x to the 4th. Okay, all of those are considered polynomials. All right, so if the degree is odd, you know that one end is up and one end is down, okay? If the leading coefficient is positive, then as far as the arrows at the end of the graph, it basically would look like this. Imagine we have that coordinate plane, okay? The ends of the graph would look like this. The left end would be down, the right end would be up, okay? When it's an odd degree, positive leading coefficient. All right, but how can we describe that? Well, we can say as x approaches infinity, so remember, x is approaching infinity in that direction, y is approaching infinity. As x approaches negative infinity, y is approaching negative infinity. Okay? Now, if the degree is odd with a negative leading coefficient, basically that negative in front is just going to reflect that graph over the x-axis, and so now your left end is up and your right end is down. Okay? So now, as x goes to infinity, y is going to negative infinity. As x goes to negative infinity, y is going to infinity. Okay, now, even degree.
Rashawn Holmes to the front office. Rashawn Holmes to the front office.
If the polynomial is an even degree, so that would be like x squared, x to the fourth, then either both ends are up, and if the leading coefficient is positive, then both ends would be up, okay? So it looks something like this. So we would say, as x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches infinity again, okay? Now, if the leading coefficient is negative, that's just going to flip that graph over the x-axis. So now both ends are going to be down. Okay, so the way we can describe that is we can say as x approaches infinity, y approaches negative infinity. As x approaches negative infinity, y approaches negative infinity, okay? Now, if you look at this notation, the only thing changing is what y is doing, okay? So you can see, like, with an odd degree, your ends are going in opposite directions, okay? And then with an even degree, either both ends are up or both ends are down, okay? All right, so let's look at these examples to find these limits. For f of x equals 4x to the 7th minus 18x cubed plus 9, evaluate each of the following limits. This is a polynomial, so you want to be able to recognize that, okay? All you need to know is the degree and your leading coefficient, okay? The degree is odd because it's 7, and the leading coefficient is positive. So it's odd and positive. So as x goes to negative infinity, y goes to negative infinity. So this would be negative infinity. Okay. All right. B, the limit as x goes to infinity of f of x. Well, that's our other end behavior. As x goes to infinity, y goes to infinity. Okay. Now, let's look at number 2. Now, you got to be careful on this one. The degree here is actually 2. That would actually be our leading term. So, if the degree is even, a negative leading coefficient, then to find our end behavior, even degree, negative leading coefficient, we're using this. Okay, both ends are going to be down. So actually, you know that both of these are negative infinity because both ends are down. Because it's an even degree, negative leading coefficient. Okay? All right. Now, if the function is a rational function, so remember, those are the ones with the fraction bars, or like your parent graph is 1 over x. These are the graphs that have the vertical asymptotes and the holes, okay? But they also have horizontal asymptotes. And it's the horizontal asymptotes that determine the end behavior, okay? There are 3 scenarios that can occur with your horizontal asymptote. Here's number 1. If the degree of the denominator is bigger than the degree of the numerator, the horizontal asymptote is the x-axis, which is y equals 0. Okay, which means the answer to the limit would be 0. Okay, second scenario. If the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. Okay, that means your answer to the limit is going to be positive or negative infinity. Okay? All right, third scenario, if the degrees are the same, the horizontal asymptote equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. And that would actually be the answer to the limit, whatever that value is. Okay? So as long as you know these three rules, these are actually pretty easy to find. Let's look at some examples. Okay. In order to evaluate these limits, we want to find the horizontal asymptotes of the function. So anytime you notice this, I want you to think end behavior. And then if the function is rational, you want to use those three rules. Okay, so we're comparing the degrees. The degree of the numerator is 2. The degree of the denominator is 2. So if the degrees are the same, you go to your leading coefficients. 2 over 4, and of course we could reduce it. This is equal to 1/2. Okay. Basically, this graph has an HA of y equals 1/2. Okay. Your horizontal asymptotes basically tell you what your end behavior is. So at the end of the graph, your y values are approaching 1/2. Okay. And that actually would be the same if x was approaching -infinity. Okay, you get the same answer. All right, let's look at number 2. To find the limit as x approaches -infinity, again, we want to compare our degrees. The degree of the numerator is 1. The degree of the denominator is 2. So when the degree of the denominator is bigger, that's when the HA is automatically y equals 0, which means that's the answer to your limit. Okay? And the limit as x approaches infinity of this function would also equal 0. Okay? All right, now number 3. The limit as x approaches infinity of 2x squared plus 4 divided by x plus 5. If we compare the degrees here, the degree of the numerator is 2, the degree of the denominator is 1. Okay, so that tells us there's no HA, which means the answer to the limit is either positive infinity or negative infinity. Now, to tell which one it is, all you have to do is focus on these first terms, okay? So think about if you have 2x squared over x, okay? That would simplify to just 2x. So think of the end behavior of 2x. That is a linear equation with a positive slope, okay? So something like that. So the end behavior as x approaches infinity, this would approach infinity. Or you can think of it like this. If you plug in a really big positive, okay, you would end up with a positive number in the numerator and a positive number in the denominator, and a positive over a positive is positive infinity. Okay, so you could think of it either way. And if x was approaching negative infinity, you would think about plugging in a really small number, but a negative number. Okay? All right, now, sometimes you'll run into limit problems like this where you have these square roots, but they're not a whole lot different than what we were doing back here, okay? Remember, your end behavior is determined by the leading term, okay? So, first of all, I'm going to rewrite this a little bit. Our numerator is the square root of 3x squared plus 6. All over. I'm just going to switch those around. Okay? Your end behavior is determined by your leading terms. So these right here. Okay? So we're just going to kind of ignore the plus 6 and the plus 5. Okay? So you could think of this basically as the square root of 3x squared over negative 2x. Okay? Well, the numerator would be the same as square root of 3 times x, because the square root of x squared is just x, over negative 2x. Okay, so that's basically going to reduce right there. So now notice that we end up with square root of 3 over 2. Which basically would be the answer to your limit. Okay, we basically end up with degrees. Another way you could look at it is we end up with degrees being the same. The degree of the numerator is 1, the degree of the denominator is 1. So if the degrees are the same, you go to the leading coefficients. Okay, now this is kind of a shortcut method, I will tell you, to evaluating these limits, but I personally find it an easier way to do it. Okay, now, here is one other thing we have to consider. Since x is approaching infinity, when we evaluate that square root, I just forgot the -2. Sorry, there we go. When we evaluate that square root, we want to take the positive root because x is approaching positive infinity. Okay, so we know we would take the positive root. So this actually would end up being negative because we get square root of 3 over -2, which basically is negative square root of 3 over 2. Okay. All right, now let's look at this second one. We have the limit as x approaches negative infinity of the square root of 3x squared plus 6 divided by 5 minus 2x. Same function, okay? So basically we're going to do the same thing. I'm going to kind of rewrite this. I'm just going to switch around that denominator to get my leading terms over each other. And then remember, your end behavior is going to be determined by those leading terms, okay? So we have square root of 3x squared over -2x, okay? Now, we are going to, again, if we simplify that numerator, that could simplify to the square root of 3 times x, because the square root of x squared is x, over -2x. Okay, so you might be thinking, all right, well, our degrees are the same, okay? So we're going to go to our leading coefficients. But since x is approaching negative infinity, we want to take the negative square root, okay? So this would actually equal negative square root of 3 over 2, which will then become positive square root of 3 over 2, okay? Or think of it like this. Once you get here, you could think of plugging in a really big negative number, okay? Even if I plug in a negative in my numerator, it's going to become positive, because when I square a negative, it'll become positive. And then if I plug in a negative into the denominator, I'm going to have a negative times a negative, which is going to become positive. So there's a couple different ways you could think of it. But since we are evaluating square roots, if you kind of pay attention to whether x is approaching infinity or x is approaching negative infinity, that kind of indicates whether to take the positive root or the negative root. Or again, just think of plugging in a negative number for x to see what that sign is going to work out to be. Okay, and again, this is kind of a shortcut method to doing this, but it works because your end behavior is determined by your leading term. Okay, and if it's a rational function, again, we're just looking at the leading term of the numerator over the leading term of the denominator. Okay? All right, so we're going to stop there. We're going to practice this more in class tomorrow, but definitely study those rules. You want to know the end behavior of polynomials, and you want to know the 3 rules for finding horizontal asymptotes, okay, of rational functions. All right, and I will see you tomorrow.